Hi, everyone. That seems like not, well, might be everyone. I don't know. It is true that there is no quiz today. So there's some Halloween candy over there. If you didn't get any during the exam, you can prioritize yourself. Otherwise, I kind of think that the last lecture took more than one per, so there might be a deficit again. So what I want to do today is just keep working on exercise C. So that wasn't on the midterm, but it definitely will be on the exam, despite the fact that we, again, got assigned, supposedly, at least, got assigned a lot of rooms for the exam. But hopefully that will be kind of more expected unless U of T administration decides to throw more curveballs at us. So please do exercise C. I'll give you, I think some people have done it already. So I'll give you like 2 minutes to kind of just get acquainted with what's going on. And I will then show something, and then I will let you do a little bit more work on it by yourself. So 2 minutes. All right. So I want to kind of maybe get you going a little bit. This is a website that lets you visualize what's going on, and that helps some people. This is just pythontutor.com, and you can enter whatever you want. So here's what's going on. So here what we have is the list L, and what it shows is L has two elements. So one element is just the list 5, 6. So L at 0 here is a list 5, 6, and with an arrow it shows that L at 0 is really the address of this list 5, 6. And then the second element is just 7. So one thing that Python Teacher doesn't show here is that really it should be like an arrow to 7 as well. It's just that because the content of an integer cannot be modified, it just says 7 directly instead of showing what's actually going on, which is that L at 1 is the address of the cell in the memory table where 7 lives. So, okay, so that's like that. So now it says L1 is a new list. And in this new list, we have the element L at 0. So L at 0, we're not copying L at 0. So that means that all we're doing is we're getting the address L at 0. So that means that in here, sorry, skipped one. So that means that in here, what you have is a new list, L1, but L1 at 0 is the address of this same list, the 5, 6. So this is why when you're saying L1 at 0 at 1 is 7, what's going on is the 7 gets placed here. So this is L1 at 0 at 1, but this is also L0 at 1 because it's just the same list. So that means that the 6 becomes 7. So now here what's happening is a new object is created, and this object contains the number 7. So first create a new object, and then L1 at 0 used to be the 5, 7, and now it's going to be the new object. So that's going to be like this. So it used to be 5, 7. And now it just becomes a new list whose contents is itself a list, which contains 7. And now, of course, what's L? Well, L is, this list, 5, 7, and then 7. So that's what gets printed. What's L1? Well, L1 is a list that itself contains a list that contains 7. Did they say that I'm on YouTube? Yeah, I did. Yeah, okay. So that's like that. So now let's go back to the worksheet and work out the actual thing. So the reason I want for people to work out the actual thing with the addresses is that this is like obviously correct, but it's hard to, for example, say, okay, like, why is it exactly that when you're saying L1 is the list that contains L at 0, why is it that what's happening is this kind of thing where you're pointing to the same list 5, 7? With the memory table, it's kind of more transparent because there are actual rules about how the memory table works. It's harder to formulate rules about how the arrows work. So let's try to work out the memory table that corresponds to this, and then we'll connect it back. All right, so I'll give you like 5 minutes. And you can talk to each other, unlike during lecture when I'm talking. So, yeah. How many people are not done writing out the addresses, actually? Oh, okay. Yeah, so several. Okay, so I'll give you maybe less. So how many people are done, I should have asked? Okay, there's like a set of people who are neither done nor not done. I'm not sure that's how logic works, but... Okay, so yeah, okay. We'll compromise on 3 minutes and then we'll do it. But I really encourage you to try it yourself because seeing me do it is not kind of super useful, actually. It's much more useful to try to do it yourself. So, okay. So I kind of rephrase the rules again, right? So what are the rules here? So to create, if on the right-hand side you have a new object, you got to create it, put it in memory. So RHS right-hand side. Assignment, so by assignment I mean equal sign, it always copies addresses. And then where do you copy the address? Well, to the variable table if on the left-hand side is a variable, and then to the memory table if on the left-hand side is an element of a compound object. So if it's an element of a list, then the assignment goes into the memory table. If on the left-hand side is a variable, then that goes in the variable table. So here on the right-hand side is a list of lists. So first we need to actually create the 5, 6, and 7 are maybe already in memory. If not, then we'd put them there. So now we need to create the list 5, 6. So that's, oh, stop. So the list 5, 6, that would be at 1020, at 1040. So that's just a list that doesn't have a name. Now that we've created it, we can create a list that's 5, 6, and then 7. So the first element would be at 1080, the list we just placed in memory. And then the second element is just the 7, so at 1060. Now that we have that, we can say, okay, L is this guy. So now we're saying L is this. So what's happening here? It's a new list, so it has to be in memory. The first element is L0, so always copy addresses. So L at 0 is this address, so we just copy it to the new list. So at 1080. So we just copy this here. So it's as if we had said L1 at 0 equals L at 0. Right? So we just copy the address here to the left-hand side. So in here, it looks like this, right? So here we're saying, okay, so the first element was, this guy. So that means that we just copy the address from this to the new list over here. So that's what happens is this address and this address are the same. And here the addresses are visualized with arrows. So this arrow points to where the list at this point 5, 7 lives. Go back a little bit. All right. So, okay. Yeah, so actually 5, 6. So, okay. So that's like that. So now we are just assigning, so copying the address of this, right? So this is now 1060, but when you're saying L1, which is of course at 1080. So L1 at 0 is just saying, sorry, not 1080, of course. So at 1200. So L1 at 0 is this guy. So it used to be 1080. And now it's going to be whatever is the address of the right-hand side. So 1220. And the outcome is the same. All right. So the rules are, again, kind of, if you don't see a new object being created, so here you're creating one object, but you're not copying L at 0, then it's got to be that an address is being copied. And that's really the only insight that you need. So if you do it, so if you draw the arrows, again, you can follow the rule, right? So like if here, so here you have a new list. So those square brackets indicate that you're creating a new list. And then L at 0, you just copy the address. You always copy the address unless you're explicitly creating a new object. So you can kind of follow it, or you can follow the rules. Or like what I do is really neither of those things. So what I do when I look at code is I say, okay, so when I'm doing this, did I create a copy of this list 5.6 or didn't I? And if the answer that I didn't, then I just say, okay, like this list used to be 5.6. Well, now it's got to be that it's 5.7. And I say this list in this because I'm basically thinking of this guy. When I'm just looking at the code, I'm saying like this 5.6, it's as if it was here. I didn't create a copy, so that means that I got to be changing this number. All right. In the same way, when I'm saying like L1 at 0 equals 7, well, did I create, like, is L1 separate from L? Well, yes, I created a new list here. Happens to have the same elements now, but I created a new list. So if I change the contents of this new list, what am I changing here? Well, I'm changing this element. Right? And then I would say, well, I'm changing this element. Well, that doesn't affect L. So that's kind of how I think. It's, I would say, a little bit nebulous. I would say that following the rules is like a more sure way. I understand that the rules are also a little bit hard to follow, but those are the rules. But really, if you just do this, so like only create objects when explicitly told to, and then everything else is copying addresses, there is not a decision there about where the address goes. So if you just follow the rules to the letter, you'll get there in terms of predicting the output. It's not easy, kind of, you would need to practice. And I would say if you practice enough, at that point, you would just be able to read the code and do what I do, which is say like, did I create a copy of this list or didn't I? Different people, like for different people, also different things work, but some combination of this would work. So for the exam, you should practice that. So, okay. So I want to now do something that's kind of related, and that's slicing. So basically, slicing is something that's kind of straightforward once you know about for loops. So if you have a list, let's say something like this, what you can do is you could say for I in range kind of start up to end and steps of step. And you can say like L1 append L at I. You have to initialize L1 to be empty. So what would it do? It would create L1, which is like L at start, and then L at start plus step. And then L at start plus step times 2. And so on. So slicing is basically a way to make shorthand for that. So you can instead say L1 is L starting from start, going up to the end in steps of step. So this is just this. Right? So you can also have like negative steps. So you can do like, so that's the same process as here. So you can do something like L from 4 to 1 in steps of -1. And that would be like L at 4, L at 3, and so on down to L at 2. If you want to go down to the very beginning, there's something special there. So you can omit if step is 1. So L1 to 5 in steps of 1 is the same as L from 1 to 5. So you can also omit start and stop. So L1 up to the end is L1 up to length of L. So L from 1 up to length of L in steps of 1. L up to 3 is L at 0, L at 1, L at 2. And you can do something like L from 4, 3, let's say, down to the beginning in steps of -1. So here you have, because like this is like 3 up to -1, which is nothing. So here 3, the beginning is omitted. So that's down to the beginning. And then in steps of -1, so that's L at 3, L at 2, and so on. All right. So in particular, L like this is just L at 0, L at 1, and so on up to L at length of L minus 1. So that means that L everything I sometimes say, or sometimes say L copy, is the same as L dot copy. Right? Because that's what L dot copy does, is it creates a new list whose first element is L at 0, second element is L at 1, and so on. So as you remember, that's a shallow copy. And that's because if L is, for example, 1, 2, and 3, then L copy is L at 0, L at 1. So you never create a copy of 1, 2. It's just that you're saying this is L at 0, so you copy the address of L of 1, 2 down here. So if so this is something we've done. So if you say L1 is L dot copy, then L1 at 0 is at 0 equals whatever, 5, means that L at 0 is also 5 now. Because L at 0 is an alias of this guy. Make sense? So that's what a shallow copy means. Make sense? Questions? Yeah. Yeah, so we'll do that. Yeah. So the question is like, can you? And the answer is you can do anything, right? So you can do something like this. So that's its own thing. I think that's what you're asking. Yeah, like that's its own thing. In fact, you don't even have to, like, it doesn't have to involve L. You could just say 12. That also works, right? So like, you can change anything to anything. So in particular, you can do this, and in fact, that's what I'm about to do. So let's say that you have L, and L is 1, 2, 3. So if you want to create a deep copy, well, what you can do is you can say, all right, so I'll have a new list, and the first element of that list is going to be a copy of L at 0. So not 1, 2, but a copy of 1, 2. And the second element is going to be L at 1. That's a deep copy. Now, creating this deep copy relied on me knowing the structure of L, right? So, because I could not have said L1 copy, because you cannot say 3 copy, right? So if you try to say 3 copy, that's just an error. So here, if I know that L1 is an integer, I can just say L at 1. Make sense? But if I don't, then that's a problem. In fact, it's a larger problem. So let's say that the list is like something like this, right? So first of all, what's going on here? Well, I have L at 0 is this guy. And then L at 0 is this guy. And that's the empty list. I can append to it or something. And now L is this. Right. So, okay. So obviously, like if I do a very shallow copy, well, let's just say kind of alias first is L. So obviously, like if this is like this, and then I go whatever, like alias at 0 is equal to 5. I run it, and now alias is this, right? So what happened is we took this guy and we said L at 0 used to be this, and now I just want it to be 5. And now alias is like this, and L is like this as well, because L and alias are just the same thing. So let's reset L. And say, okay, so what about a shallow copy? So that's going to be like this. So now if I say shallow 1 at 0, that's going to be this. And I'll say shallow 1 at 0 is 5. So now shallow 1 is this, but L doesn't care. And that's because shallow 1 and L are two separate lists. Right, so I change shallow 1 at 0. That's not the same as changing L at 0. However, if I go back and say shallow 1 at 0 is equal to 5, then L is this, and shallow 1 is this as well. So why is that? Well, because shallow 1 and L are separate lists. So you go shallow 1 at 0, well, you change shallow 1 at 0, not L at 0. However, I've never created a copy of this guy. So this guy exists only in one exemplar. So I change the empty set to be 5. Then I just change the first element of the inner list to 5, but that means that that affects both shallow 1 and L, because while I created a copy of L, I created a copy of this list. The first element in both copies is just this guy. There's only one copy of it. Makes sense? So, okay, I might say, okay, start from scratch. So I'll do like shallow 2. And how would I do it? Well, now I need to make a copy of L at 0. And I'll place this copy of L at 0 inside a list. So I create a fresh list, and its one element is L at 0 copy. So that's going to be like this. And shallow 2 is going to be like this. And now if I do shallow 2 at 0 equals to 5, this is shallow 2, and this is L. So why is that? Well, I created a new list whose first element was a copy of this guy. So I took this guy and I copied it. So now there's two lists, both of which contain this guy. And I changed one list, but not the other. However, oh, I need to append. Okay, I'll change this to a 0 so that it's easier and I don't have to append. What? Okay, so wait, that's 5. So I just need to run it in order and it's going to be fine. So I'm not going to run this because that makes it so that the list that contains 0 is now just 5. And now I'll set this to 5. So now shell 2 is this. And L is also this. Right? So to restart it, so I run those 3 lines, and L is this, and shell 2 is this. Right? Why is that? Well, it's because I made a new list whose first element is a copy of this guy. So that means I have 2 lists whose contents are this guy. But I never made a copy of the inner list. So there's only 1 copy of the list that contains 0. And then there's 2 copies of the list that contains it. Make sense? So, okay, so now how do I fix it? Well, I'll again have this L, and then I'll say, okay, L is this, and then deep is going to be a copy of L at 0 at 0, and now I need to also enclose it in another pair of brackets so that now I'm creating a list whose first element is also a list, and then I'm making a copy of this guy, and that's the inner list. Now, of course, at this point, I kind of put in so much work into this that I might as well have retyped the thing anyways. Right? So we'll see how to solve this problem, how to make it so that you don't have to manually basically input the structure of the original in order to create a deep copy, but we'll have to wait for later in order to do that. This, of course, is reasonable. So if you know that the structure is pretty simple, you could just say, okay, well, like I just got to make a copy of L at 0, and then L at 1 is an integer anyway, so I'll just make this copy by hand. That's fine. That's if the structure of the list is simple. You might ask, like, why would you care about complicated structures? And the answer is they're actually all over the place. So you should care. All right. So that's this. So I want to talk a little bit about the bonus problem on the test. So the bonus problem, of course, is like it's supposed to be kind of difficult and entertaining. I realize that most people are not looking to be entertained during a midterm, and there were other sources of entertainment as it happened, but those were not foreseen. Anyway, so the problem was basically compute pi to arbitrary precision. And the problem is that if you just look at the float pi, it has a limited number of digits, right? So you cannot compute like whatever the 200th digit of pi. You can try, of course. So like you can say like math.pi times 10 to the power of 20. And then you can 200 rather. And you can try to convert it to an integer, but those are fake digits. Those are like not the actual digits of the actual pi. And of course, you try to do it with a larger number, and Python will just say the float just cannot contain this at all, right? So just computing a float using the Leibniz formula is not going to work because it's not going to work for an arbitrary number of digits. However, the easiest way to approach this is to say, well, like a float doesn't have an infinite number of digits to store the infinite digits of pi, but an integer can store as many digits as you want. And that's kind of the approach. So that's on Piazza as well. So the basic idea is we use the same thing as what you had in the lab, except instead of floats, we use integers. So how do we do that? Well, it's the same idea as here, right? So you can have as many digits as you want if you store the thing as an integer. So what I'll do is I'll say, I'll store whatever my approximation. So that's the same thing that you had with the Leibniz notation in lab 2. So I'll store it in an integer. In order to store 3.14 whatever in the integer, I'll just multiply it by a very large number, and I'll just keep the integer part of the product. So the way I'm doing it is I'll say, okay, I'll have my factor, which would be like more than I need. So like 4 times 10 to the power of n digits. So that shifts everything by n digits plus 10 to the left. And then I say, okay, so pi, I'll just add this term. So that's the Leibniz formula, like minus 1 to the power of I divided by 2 times I plus 1. So one thing to pay attention to here is that you cannot make this be a float because a float has limited digits. What you can do is you can say, okay, I'll just make it an integer that has a lot of zeros at the end. So that's going to be like either 1 0 0 0 0 or like minus 1 0 0 0 times 4 because we have a 4 in a factor. And then we'll do the division by 2i plus 1 using integer division. So if we multiply by a large enough factor, then it doesn't matter that the division isn't precise. The reason we have to make it integer division is that if you don't, so if your factor is very large, like 10 to the whatever, 500, and then you try to divide it by whatever, Python is, this is times, Python is just not going to allow you to do it because this is too large, you cannot store it as a float. However, if it's an integer, it's all fine. You just do divisions of 2 integers, the result is an integer. Those can be as large as you want them to be. Right? And then what we have is basically the term that we need in the sum anyway, but multiply by the factor. All right. So when do we stop? Well, we stop when the last digit doesn't change. So if the difference between the last pi 10, so that I just update last pi 10 with kind of the last estimate, and the current pi 10 is like smaller than 1, then that means that we're done. Right? Because kind of the 10th digit after the last digit that we actually need is now not changing. Well, at that point, it's precise enough. So if you run this, that is what it looks like. So it converges pretty fast to the first 4 digits. Then it starts having issues, but that's fine. Like you didn't have to run it during the midterm, you just had to write it. Right? So eventually it'll get there, not very fast at all. Like the Leibniz formula is actually quite slow. But so you need a lot of terms. But eventually it'll get there. So this is like pi times 4 times 10 to the 60. Right? And then once the last digit stops changing, well, for sure you can get the first 6 digits. Make sense? So that's kind of the difficult part, is you have to figure out, so that's one way to do it. You can do it with lists or whatever as well, but that's just more difficult. So you just do an integer, and the integer store the digits that you need. Yes. well, I'll have to see. Like, I never want to promise like on the spot what's gonna happen because you have to look at like the individual solution. So I believe that if you don't add 10, then it's not gonna work exactly. But like, if you kind of got to the solution, you kind of got to the solution. So we'll have to see kind of what's going on there exactly. But yeah, like you should get at least most of the marks. So okay. So I think like basically you need like +1, but if you do +1, you got to be careful there about conversions for a small number of digits. Yes.
Is there a certain number of digits that string can hold?
No, well, I mean, like a computer cannot hold an infinite amount of information. So if you run out of memory, you run out of memory. You can't store anything, but there's not a fixed limit. Well, I should say. There is in practice a fixed limit, which is like larger than what you could store in memory anyway. So the indices that you use in order to index a string might be limited, but by a very, very large number that's like larger than what's practical to store in a computer anyway. So, okay. Yeah, so I think it's getting the 5th digit now, so like progress. All right. So now it needs to be like slightly annoying in order to actually get the digits, because now you have this integer, which you know is 16 figures. So now you need to get like the first, second, third, and so on digit. So like multiple ways of doing it. You could, for example, take pi 10 and then divide it by 10 to the 16th, and get this divided by 10 to the 15th, and so on. All right, so multiple ways of it. Okay, all right, so that's that. Like, obviously, again, kind of it's the bonus question, so like you didn't have to do it to get full marks. So it wasn't supposed to be easy. We'll start marking. So the midterms are now scanned, so hopefully within a few days we'll get everything marked. All right, I'll see you Wednesday. Thanks. And take some Smarties. They're probably feeling bad that they're unpopular. I don't know what. Yeah.